Okay, friends, today we are going to complete this tip. So take the practical tube. Uh, Go to page number 3. So we discussed about random errors, and it depends on the object and the measurement. And after that, we talk about absolute error, fractional error, and percentage error. Okay. So first of all, we'll write the notes and move on. Okay. Now, uh, everyone has completed that random errors note. A random error is an inconsistent, non-reproducible variation caused by the object or the measurement process itself, which can be reduced by repeated measurements but does not require corrections or recalibration. So I said systematic errors are errors that we can't deduct them using by taking an average. We can take more readings and take the average, right? But in random errors, it's the exact opposite of systematic error. We can correct it by taking more readings and taking the average, but we can't recalibrate or we can't do a correction to the final reading like we did in the systematic errors. Understand? So in systematic errors, zero error is included in the systematic part. Why? We are adding or subtracting something from the final reading, right? And recalibration is also included in the systematic error. So in random errors, we can only uh, uh, deduct it by using by taking many readings and taking the average part. For example, you take a cylinder. Let's take a metal cylinder. Okay, we are using a vernier caliper. So by using a vernier caliper, we are going to keep the jaws here, next jaw here, and we are going to measure this vernier caliper is like this type of instrument. Okay, here we can take the reading. So this is going to measure the diameter here. Understand? So what we do is we don't know if this cylinder is consistent. I mean the diameter. So what do here to deduct the random error is we take readings from here, place 1, keep the vernier caliper here and take the reading, the diameter, and keep it again here in the middle and keep it here again, and we take 3 diameters, D1, D2, D3, D3. So since we are taking 3 readings, let's take the least count of this instrument is normally it's 0.1 millimeters, right? We found it in a general vernier caliper. So let's take this is 330.30 means 3 centimeters, 30.1 millimeters E1. 1 is equals to 30.1 centimeters. And D2 is 30.3 millimeters and D3 is 30.5 millimeters. Okay, so we have 3 readings. So object, so the object is not consistent. The diameter is not consistent. The diameter has changed from place to place. So this is a random error. Okay, we have to neglect this error to go to an accurate calculation to get an accurate reading. So what we do here is we add these 3 of them and divide it by 3. It's the average. So what we do is we take an average by adding D1 and D3. So in A-level physics syllabus, normally you take minimum 3 readings to neglect a random error. Understand? So in every practicals, when you go to your schools and do the practical, in your practical book, they have given tables to write the readings of this diameter, right? So we have to take minimum of 3 readings, take the average of them. Understand? We keep it a corner again in side and some part between the 2 readings. Okay, we should take like that, right, and divide it by 3. So we would get 30.3 millimeters. Understand? Okay, right. So this is how we deduct the errors caused by the object. That means random errors. Okay. So again, if we get a small summary about errors, errors divided into two groups, systematic error, and random error. Systematic error is caused by 3 factors: instrument, the person who is conducting the experiment, and the environment. Okay. The random error is caused by the object and the process. The process is measurement. So after we take a measurement, what is the error? So we take a reading. So due to the least count, the maximum possible error and the lowest possible error is the error caused by the measurement, the process. Okay. So that least count, we did something like add or subtracting. That is a error caused by the measurement. Okay, that's not the error from the instrument. The error from the instrument in the sense the instrument had been damaged, or the instrument had been what, the scales or the divisions have been mistakenly calibrated. Okay, so this doesn't include in the instrumental errors or the personal errors. We look at it and we take the reading, right? So it cannot be a personal error. Personal error in the sense error due to our mistake, due to some factors in our eyesight, or due to factors that we are looking at it indirectly. So one of a personal error is the parallax error. So when we take a reading from a ruler, I have mentioned it, you should look perpendicular to the ruler. So you have the ruler here, okay, have calibration points, 3 scales. So here you keep some solid object. So you have to see it. This is the ruler. So you have to look perpendicular to this ruler. So your eye should be here. So if you are looking from here, wrong. If you are looking from here, wrong. So you have to look it from here, right? You will understand this when you're taking readings from, you have an experiment to do, practical in waves and oscillations in the 3rd unit. So in that unit, you use this method. You have to look perpendicular to the spring to take a reading. Okay, right. So this is the summary, and now let's write the definition for the error caused by object. Okay, start right. So you all have filled the application, keep it in the corner of this table so I can come and collect it. Okay, make sure that you have written everything in capital letters and you have filled every spaces, right? Then only I be able to give the recording. Okay, right. So let's start, right? A random deviation caused by, under the topic object, a random deviation caused by non-uniformities. Non-uniformities in the sense cylinder is not uniform. Okay, non-uniformities in the object itself. Non-uniformities non-uniformities in object itself, object itself, comma, which can be reduced by taking multiple readings, at different points, different points and averaging them, understand? So this is caused due to non-uniformities the object, and which we can reduce, okay, which we can reduce it by taking multiple readings and taking the average of them, right? Understand? So let's go to the measurement part. So which is much clearer, dark green or black color? First or second? This is one or two, just one. You online people code. They use dark green. I used 10 colors. Can you see this letter? Colors clearer than the green. Eh? Right, okay. So measurements, under the measurement part, a random deviation bounded by have two rectangle boxes, right? Now write this in first one. A random deviation bounded by the instrument's least count. Random deviation bounded by the instrument's least count, comma, whose relative significance, a random deviation bounded by the instrument's least count, whose relative significance varies inversely with the magnitude. Of the measured quantity, whose relative significance varies inversely the magnitude of the measured quantity, whose significance varies inversely the magnitude of the measured quantity. Okay, right? So it says that the random deviation bounded by the instrument's least count, the instrument's least count, okay, and it's relatively significant with the measured quantity. I said it. So the least count is not an error, but would be an error to measure small parts. You use it for like if we take a measuring instrument to measure length, the least count, let's take a least count of 1. So this least count is not an error. This becomes an error with the measured quantity. Okay, if you measure something relatively larger than 1% of this, I mean, if we compare this to the ratio, this least count should be what? 100 times smaller. 100 times smaller. Okay, 100 times smaller. That's the minimum part. So the minimum measurement that you can take from this instrument is what? What's it? It should be 100. 100. Okay. So what's the ratio now? 1:100. So the minimum should be the ratio. The minimum ratio should be 1:100. This minimum. So we take measurements. This is the least count. The least count is not going to change because it's constant for an instrument, right? So the measured quantity is going to change. The numerical part is going to change. So what we should do to not neglect this error by the least count, we should measure something 100 times larger than the least count. Understand? So if you measure something which is 99, let's take this as centimeters. Let's take this as centimeters. Take this as centimeters. Centimeters. So we can't measure 99 centimeters. Right? This is less than, now if you take 99 into 1, that's less than 100 to 1 ratio. Right? So measure this, the percentage error is going to be larger than 1%. Understand? So the percentage error, now let's write the formula to the percentage error. So if you take the percentage error, the percentage error is equal to least count divided by the reading. Can you read this? Because I'm going to write one by one. It's going to make a tick count by 100%. Okay. Now I'm going to upgrade you all to the next level. Okay, because we have to go to mechanics. So when you have an equation, okay, you should consider the constant parts. Okay. Now let's see which are the constants here. You'll know the meaning of constant. So least count here, a constant. If you take one instrument, you're going to use one instrument for one practical. Okay, now we are inside one practical, there is one instrument. So the least count of this instrument is constant, so it's not going to change. And this 100%, does it change? We take percentage of something, that's going to be universally constant. It's universal constant. Constant only for one practical. So, and this is known as a universal constant. So there are types of constant. So, but if we take one practical, we are going to take only one reading, is it? No. Said to neglect errors caused by the object, we have to take more readings. So the reading is going to change. Understand? So this is the final percentage part. Okay. So if we can make this like this, okay, you have the knowledge of units, right? So what I'm going to do is I'm going to take this. I'm going to take least count multiply by 100% is a constant. Okay, constant, right? It's a constant. So I'm using this k, make it a constant. K means it's a constant. Okay. So now what I'm going to write, I'm going to mention this as the A, as the B. Now I'm going to substitute B inside A, right? So to the percentage error, I'm going to use a symbol this. So instead of percentage error, now I'm going to use the symbol this. Okay, make the note clearer. So percentage error is now equals to what? Percentage 100 going to be K. Okay, I substituted it. Understand? Right? And that's divided by the reading. Read. This simplified version. Okay, what I'm going to do, the next step is I'm going to write percentage is equals to K to 1 over reading. I can write it like this. I separated it. Okay, according to the principle of what dimensional analyzing, I mentioned you a small step how you can change this, how you can change a proportional sign into an equal and a constant. Okay, now I'm going to do the reverse of it. What I'm going to do? I'm going to do, is this clear? Color, pink. Okay. Yeah, is it? So I'm going to change this equal mark and this constant mark as a proportional sign. Okay, a proportional sign. Proportional sign. So proportional. Proportional. So percentage error proportional to 1 over read. 1 over read. Proportional to 1 over read in the sense, inversely proportional to what? Inversely proportional to the reading. Understand? Okay. So when the reading is going to increase, percentage error is going to decrease. Want that? Want to reduce the percentage error. So we are going to increase the reading. That means the magnitude of the reading. We have to take larger readings from an instrument than taking smaller readings. Understand? Right. So that's what they are saying here. Which can be not here. Whose relative significance to the error caused by the measurement. Okay. Whose relative significance varies inversely with the magnitude. Varies inversely with the magnitude. Magnitude in the sense they are talking about this reading. Okay. Is inversely proportional to the reading. Which error? Understand? So when we are taking larger readings, the percentage error is going to reduce. So if you have a notebook, you can copy this stuff. You'll have a notebook. You can copy this stuff. Can I read it? So application you put for all levels. A levels. Okay, fine, fine. Now that you are all levels. You are now ALL people, right? Ordinary, advanced, common application. Example here. NIC number, I am a male following by streams for my ALS, right? That's why I have given you an example. That's why you have ticked the ALL. So this is the new system of, rather than giving you instructions, it's better to give an example. Okay. NIC number. Give, give it, give. Both. Okay. Two, four. So three of you haven't given the application. You'll have the phone, then you'll take 10, 10 of you. 10. Go and classes over. Try to do it. Okay. So finished. Ready. We are coming to Asham's class. Be able to write faster. Reading really fast. Easy. Okay. Biology. Next one. Everyone? Thanks, students. Write the note. Have the tute right. So write the note. If you want, you can copy it in a writing notebook. So let's go to the next blank here. Okay, next blank. Kill the first one, the next one. Okay. So there you have to write an example. An example. First of all, don't start right. You have to manage the space. Just look here. So you're going to write an example. 287 plus or minus 1. Okay. I should. This is fairly accurate measurement. Measurement is fairly an accurate measurement. Next, you have plus or minus 1 millimeter. This fairly highly accurate measurement. So now start right. Start right. Inaccurate measurement. Okay. After that, in order to compare these errors, we need to go through comma, that's all. And handwrite is this much worse. It's hard to write in a handwriting noise. So there are whiteboards, smart boards that we can use as a whiteboard. We can move it and use it as a whiteboard. I've seen stuff. If the screen is white, you can off this and use the marker. How about online people? Write this. Can't read anything, just tell me. In order to compare these errors, go through comma. So I have given the 3 points. That's it. Absolute error. What's an absolute error? That's it. Count. If it's hard to remember, just write it here itself. Dash absolute error is the least count. That's all. So it is much easier in A-level syllabus than in Cambridge and stuff. In Cambridge, they take it as least count divided by 2. You can think it by it. Because I said the maximum possible errors to go to the next or to the scale which is before the scale that you can see. Okay, Cambridge they take that and take the average of that. Like, you can think that because of that. That's because they think that the reading doesn't align with the scale of the time. They are looking at it in like a micro dimension. So it has only 2 sides, this or this. Let's say the ruler is here. Okay, we zoom it, doesn't align with this. It could be in this region or it would be in this region. So let's take that it is in this region. So the reading should be okay. Our syllabus, we take this aligns, but we are not sure. Aligns this, but we are not sure. So we take this as the maximum, this as the minimum. Those syllabus, they take this as the maximum and this as the minimum. So still there are just in A level who teach that part. So yeah, one time there was a question in practicals. They asked the absolute error. So if students learn that part, least count divided by 2, they're going to write that, right? So you're going to lose a heavy part of marks. Okay? And you have to, after asking the absolute error, they are going to give you some calculation based on the absolute error. So the questions after that, they are going to the error is going to accumulate in you. You are going to take least count by 100. So you are going to lose marks. Okay. So when you are learning theory, after you learn something, just check it with the resource book. Okay. You should have the resource book as well as the pace rules. Okay, let's go to the next page. Now we are going to define absolute error, fractional error, and percentage error. LL is much easier. Okay. Because of the resource books released in 2018. No, after 20. So before 2018, there was no textbooks for LLs. You know that? No textbooks. So how are you going to learn? The notes from the teacher. From the notes from the teacher. So you don't know from which content will the exam questions will come. Really hard to learn. So you should go to a tuition class. But nowadays, it's not compulsory. There are some rare people who take A without going to tuition class by only studying resource. For physics, for chemistry, that's okay. But for physics, you can't because you have to do a lot of sums. There are no sums. There are like 1 2 sums in the resource book. So the resource book is just to refer the theory, just to take a reference. Biology is like that. Okay, biology they are going to ask question and have to write the answer taken from the resource book. In physics, not like that. They ask questions like to solve problems. Still, there's no resource book for maths. No resource book. You have to fill your head with a big content. Yeah. So really go through and next subject. have to know everything. Okay, but can make a curriculum from the past papers. I've asked them from here to here, so they are going to ask from here, this part. Okay, let's go to the absolute error, page number 4. Start writing the note. Absolute error is the difference. Absolute error is the difference. Absolute error is the difference between the measured value and the true value. Absolute error is the difference between the measured value and the true value, comma, equal the least count. Absolute error is the difference between the measured value and the true value, comma, equal to the least count of the measuring instrument. Okay. So I think the absolute error is going to be half of the least count. So if you compare the two syllabuses, which percentage error would have a as the lowest minimum? Okay. So I said in percentage error, the numerator I said least count ne. The numerator is least count, the denominator is reading ne. But that's not the true equation. This is for A-level syllabus. True equation is this is absolute error. Okay, the absolute error. Okay, so in A-level syllabus, this is least count over reading. Okay, so if you compare two percentage errors, this is going to be L divided by 2 over R. It's going to be L over R. Okay, right? So let's take the percentage is 1. Then the reading should be solve this question. So R, you take this reading here. It's going to be L divided by 2. R is going to be L. This is 100 percentage. So 100 percentage. Got to write this. Every time this is like a unit. Okay, you have a unit. This is percentage mark is a unit. So this is 1 percentage. So it should be, to turn it to a fraction, it's going to be 1 over 100. Okay, it's going to be 1 over 100. So equals to L divided by 2 over R. L divided by R. Right. Can you see the board? Yeah. So what I'm going to do is I'm going to swap this. I'm going to take R here. Okay. So this L divided by 2 is going to come like this, L divided by 2. Okay. This 100 is still here. I'm going to send it to this part, this side. Understand? Okay. So here again, what I'm going to do, I'm going to take R here. It's going to be L to 100. Okay. Understand? So this is our syllabus. This is their syllabus. So this is going to be L times 100. This is going to be L divided by 2 times 100. So let's take a meter ruler. What's the least count of a meter? 1 millimeter. So let's put 1 millimeter here. Okay. 1 millimeter times 100, it's going to be 100 millimeters. 100 millimeters divided by 2, 50 millimeters. 50 millimeters. So here it's going to be 100 millimeters. That means till you are hard to think about millimeters, so let's turn into centimeters. This is 10 centimeters, this is 5 centimeters. So we should take readings more than 5 centimeters. To take readings more than 5 centimeters. That means we can take 6 centimeters. We can measure something which is 6 centimeters from a meter ruler. Here we can measure something greater than 10 centimeters. This is the minimum. We can't measure below this level. If we measure something below 10 centimeters, that's going to be inaccurate by a meter ruler. Understand? Here, below 5 centimeters. Now, if somebody think this is absolute error is going to be least count of 2, and he's going to take a measurement of 6 centimeter, accurate overall, which is much accurate. Which of if we choose one of this, okay, and if we take readings, which reading would be much accurate part, right? Understand? So there's going to be a much problem here. They have choose this to take some easiness measure, like to measure something below 10 centimeters, we can't use a meter ruler, we should use a vernier caliper. Okay, phone is more than 10 centimeters, right? We have a ruler. Take a ruler. Ruler is much lengthy than this. Yeah. Yeah, this is going to be larger than. So we can measure the length of this one, but the width is going to be 8. So we should use a vernier caliper. Understand? There are some that you all don't know, should learn. Understand? Okay. So you all know the dimension of when you're buying a phone. If you're going to look at the specifications, they're giving the height is this, length is this much, and the width, that's accurate to the millimeter. Yeah. So they measure by a vernier. So if you are going to become an engineer, you have to know the skills, measure this stuff. Okay. Right. Now let's go to the fractional error. So it's perfect. What's an absolute error? Have a clear idea. Is it? Okay. Right. Okay. Let's go to fractional error. So we should be much speeder than much. We should be able to write quickly. Fractional error is the ratio. Start right. Fractional error is the ratio of the instruments. Fractional error is the ratio of the instruments. Maximum possible error inside brackets least count. Fractional error is the ratio of the measurements. Maximum possible error brackets least count. Least count. To the measured value. Full stop. Fractional error is the ratio of the instrument's maximum possible error inside brackets least count to the measured value. The measured value, right? After that, you have a small box above the percentage error. Inside, you have to write fractional error is equal to error of the instrument. No, wait, it should be absolute error. Absolute error of the instrument. Okay, should minimize. You should measure the size to write this. Count mag here magnitude of measurements measurements. So all school teachers, they know to write italic. What's this known as? Writing. What? Cursive letters. So the English medium was introduced after 2000, I guess. So you can write. Start write. So students who were writing on those days, they were old school people. So in those time, British, due to the British influence, everybody who is doing the exam was writing cursive. Cursive is much easier to write, so you can write much faster than writing normal letters. So they were using cursive letters to write the answers. So the examiners, there were a limited number of English medium, but they didn't have the knowledge of cursive letters. So cursive letters, the one who is going to write the cursive letter should have the knowledge, and the one who is going to read should have the knowledge. It's not cursive letters. Cursive letters are much. So you write A or something like this, or like O A. Everything is like same part. So it was really hard. And after that, from the examination board, they banned students to write cursive letters, to use cursive letters. Still can't use cursive letters. Write answers in the exam, government exams. They don't go to practice it, right? One of my friends practiced. He was in problem. So he wrote the notes from cursive letters, but when he was going to write the exam, it was a little bit hard to him. So since he is he was a max student, so it was easy. Max, you don't have that much to write. If you are a bio student, if you get practice to it, you're going to be in trouble. So you have that skill to write a cursive letter. That's a skill, okay? So when you're writing novels, publications, finished, wrote this. Should have that knowledge. So after that, you have the percentage error. Okay, percentage error. Try the note. Read anyway, just tell me. Absolute error of the instrument, least count, magnitude of the measurement. I can make a rectangular box and make it nicer, but waste of time. Percentage error. Okay. I haven't given that. So write this absolute part, right? I haven't given this. Write the absolute part. Write this absolute part. I haven't mentioned. Should be absolute error of the instrument, not error of the instrument. So next, given that. Percentage error. So it's easy. Write it. Fractional error is the ratio of the instrument maximum possible error. Wait. Don't start, right? I have copied the fractional error here. It should be 3 words. Percentage value of the fractional error. Percentage value of the fractional error. Right? Percentage value of fractional error. That's all. The difference between teachers and lecturers. But translate ST and translate ST. Another. They come. They don't guide you. Express their knowledge. But teachers, they have to look into your are you writing correctly? Are you doing the problems, solving the problems correctly? So when you are going to university, you are going to be in real trouble if you are not a self student. If you are self student, able to gather knowledge from me and search about it. Okay, not just following them, not followers. You can follow a lecturer, but they are not going to instruct you. Do like this, do like this. Come, tell the theory. Okay, so it's really boring to be really boring. Unless the lecturer is a little bit unless if the lecturer has a little bit humanity, he's going to like this how we are going to access the things, and this is how to research. They'll give you instruction. But if he's a senior lecturer, head of the department, hard to manage. I can't tell that, but they are really strict. If you are going to be in medical faculty, the lecturers are doctors, not doctors, they are consultants. Consultant in the sense they are doing special, and they are they are learning for like 9 years continuously. They have eaten that much like it's a little big pressure. You have to learn 9 years as well as go to interns in hospitals, in government hospitals as well. I think you should go to government hospital. Mm, Hospitals in Sri Lanka, really traumatic life. I've been in hospital. I was in hospital in for like 2 years. I was not a doctor. I was I was staying with my father. I knew the whole map of general hospital in Ratnapura, and every doctors I know, every nurse know me. Yeah. So being, I was a patient, right? But I can sleep. Right? If it's night, I can sleep. But when I'm sleeping, like it's 12 o'clock, I'm sleeping. So suddenly a doctor comes. I'm being with a patient, no? So one who are being with a patient, they can't sleep. That's the rule in. So they are going to wake. Look at the patient. Going to gonna go to washroom, help him, like that stuff. So from that, I got a trauma. That means whenever still I have that. When I'm sleeping, when I heard some noises, I just wake up suddenly, and my what whole body begins to shiver. Okay, so if you are going to be a doctor, you have to be 24/7. Only for 5 days when you are an intern, harder, really hard. You have to give something for doctors, Sri Lankan doctors. But after you become a consultant, like doctors are people who not normal doctors. Consultants are people who work a strict schedule. Strict schedule. Wake up, brush the teeth, go to hospital, come. Strict schedule. They hate ones who disturb that schedule. Consultant. They are really there are good personalities. They have policies. They are like superhuman, ultimate part of humans. So have a dream to be a consultant. Okay, right. Uh, so you have the equation for percentage error. Okay, it's error of the instrument, again the same as the fractional error, but multiply by 100. Okay, so whenever you change a fraction into a percentage, you multiply that fraction by 100. Remember that. Okay, more trick. So let's go to the next page. So we have given an example. Find the fractional and percentage error for the following reading, for the below reading. So the reading is 205 millimeters plus or minus 1. Okay, so they are saying to find the fractional error and percentage error. Fractional error, fractional error is going to be, what's it? Discount over the reading. This also millimeters, this also millimeters. So these millimeters cancel off. The fractional error is going to be, I have given it, so I don't want to calculate. So it's 0.0048. Okay. So the percentage error is percentage error is equal to 0.0048 multiplied by 100. Why did I multiply by 100? Because this is the fractional error. That one multiplied by 100 is the percentage error. So 100 is going to come here. Zeros, the decimal point. So it's going to be 0.48, but over 100. So this over 100, over 100 means out of 100 is 0.48. So what we do is take this whole part and write it here. What? How do we write it? Understand? So we delete this part. The meaning of this percentage. Okay, remember that. The symbol. So in old days, if you just if your father is going to teach you mathematics, they are old people, 90s kids. So when they are telling you to, when they are teaching you to how to add fractions, they are going to write fractions like this. Have you seen it? They don't write like this. Write like this and over 30. So in old days, they use that method. This method. So that's why the percentage sign like that. It's going to be 1 over 100. So they have changed it. Something here and something percentage. Right. So you have some important point when you are doing a percentage error. Sorry, not errors. Important points related to errors. Okay. The first point. That's the really important point. Okay. Read it while I'm reading. As we usually require error to only one significant figure, last two values given above would be used as 0.005 or 0.5% respectively, and then when explain it. But you have to keep the error only to one significant figure. What's a significant figure? What's a figure? Numbers. So mainly they focus on numerical numbers other than 0, 1 to 9. So you should keep the error with a significant figure which is between, not between from, not we use the word between, we can take one from 1 to 9. You can only use 1 to 9 to express an error. There can be zeros in front of these numbers and a decimal point, but you can't put another significant figure. So you have in error, how did you mention the fractional error? 0.048. So you have two significant figures. You can't write it like that. How do you want to write? You have to write it as 0.005. You have to round it off. So when they are asking a question, find the fractional error, you have to find it as 0.48 and this mark, no, this mark it as 0.005. So they give marks to this, not to this. Understand? So keep this in mind when you are writing answers to practical questions. Okay, this is a seminar, so I'm only the theory, but there are some small examples. So I'm not going to do practical questions. What I'm going to do is I'm going to keep a night seminar. I'm going to give some papers, not tudes, to institute. So you should collect it before you are attending the night seminar. You have to keep it with you and you can attend it's an online. Well, so I haven't still scheduled it. It would be mostly like after 8 p.m. or 7 p.m. It's going to be like 2-hour sessions for 2 days or like that. So I can cover practical questions from that. So I will give same like from this lesson, there's only one question in practical structure. They say you have 4 questions, this is on 1 question. So focus to 1 question. You don't want to do a lot of problems. So that's why a lot of teachers waste time doing questions. Understand? So what you have to do is you have to take the past paper. So I think I would be able to provide you playthrough books. I'll look into that. So what you have to do is you have to attend the night seminar if you have to have a practice on doing physics question. To do physics, to face the exam in physics, you have to have practice. You have to practice questions. Okay, but if you have a good knowledge how to solve questions, you don't have to attend that. Okay, if suddenly you can solve a question by only doing 1 example, that's the best. Okay, to do 1 example, you should know how to do 100 more examples like that. Okay, so I'll give you like, I cleared that, right? So I gave, here the example was 205 plus or minus 1. So what I'm going to do is I'm going to use this exact question and change this number. I'm going to change this as 362 and this one as plus or minus 0.01. So you should be able to do exact things. This stuff, substitute them and to find the answer. So what you have to do is you have to do max part. Just what's the difference here? You're going to do max part. So you should be able to recognize the pattern in a question and copy paste into your mind. Understand? So from that you can reduce it. So whatever the questions you do the questions with the right mind, not with like I'm doing this illegally. Don't do that. Still, when I see some questions, I can recognize if this is from the past paper or this is just a question from a model paper, and I can mention from which year is this question is from. Have them. You should be able to do. I'm a max student, not a bio student. So bio student, usually bio students have a good memory. Okay, so that's how you do a question. So in the night seminar, I will do some questions and leave you some questions if you can. So this is the first time like you are introduced to the learning. So I'll give you some questions to do. Have much leisure time than other people, so you can do some questions. Okay, right. So the second point is the accuracy of the measurement is considered sufficient if the percentage error is 1% or less than 1%. Highlight that part. What? If the percentage error is 1% or less than 1%. The second point. The important factors. The second point is accuracy of a measurement is considered sufficient. Highlight from if the percentage error is 1% or less than 1%. So I thought of bolding those letters, but when I bold them, you don't do a work, right? This is bolded. So you forgot that stuff. So mainly the best part to learn is by writing notes. That's the best. Okay. So I have given the tute. So it's a little bit boring. You don't have much to write. So that's why I am also saying give something to write. So I'm not going to give you bolded letters again. I'm going to tell if you have to highlight or not. So if you highlight or you can underline from pen. So you don't remember that part. The percentage error is 1% or less than 1%. Online people, which topic should I write part? Which part? Yanuka. Now okay. Right. The third point. When we use a meter ruler for measuring a length of 100 millimeters, when we use a meter ruler for measuring a length of 100 millimeters, the percentage error is 1 over 100 multiplied by 100 is equals to 1%. But what they have done is they have used the percentage error formula. 1 is the least count in a 1 milliliter is the least count of the but meter ruler. Okay, so 100 should be the reading. We have to have percentage error as 1. Okay, that's what they are saying. Therefore, the accuracy provided by a meter ruler in measuring a length which is less than 10 centimeter, 10 centimeter means this accuracy of the measurement that is less than 10 is not sufficient. Okay, less than 10 centimeters is not sufficient. In such a case, a measuring instrument with a least count less than 1 millimeter should be. So in such a case, when you're measuring lesser than 10 centimeters, you have to use a measuring instrument which has a least count lesser than 1 millimeters. So it's a vernier caliper. Understand? 0.1, that's a vernier caliper. Okay, you have to use a instrument with a vernier principle. Not it should be a vernier caliper, it can be a traveling microscope also. Traveling microscope use the exact vernier principle. Okay, right. Less than 1 millimeter. For these instruments which use the principle of vernier or screw is required. So screw, there I said there are two principles, right? There are two principles. Principles. One is the screw principle, screw. This is a screw, and the next one is vernier. Vernier. Okay? Vernier. Understand? So screw principles, that's a little bit different principle. I'll go to that part today. Right. So to the next point. When calculating the value of a quantity y given by y equal a n, y equal a to the power n t, when you're calculating something, Okay, the error of A influence much more than the error of B. So this N belongs to this A, not this B. N. N belongs to this A, not the B. Okay, so let's take Y is something volume. Let's take Y is volume of a cuboid. Volume of a cuboid. Volume of a cuboid. Okay, so let's take toothpaste box. Toothpaste comes in a box, cuboid. So it has a square and a rectangle, right? So length into breadth, height. So the breadth is same as the height. I'm going to put height here. Understand? That's a square. Square cross-sectional area into the length. You know to find the volume of a prism. You know prisms have triangular prisms, circular prisms, and square prisms. Circular prism is a cylinder. Okay, so this is a prism. So this is going to be h squared into L. Okay, fine. So the error from this has a power 2. This doesn't have a power. That's 1. So the error from the length, sorry, the error from the height is going to influence this volume much more than the length, the error from the length. Okay, if there's an error from the length, it's going to just affect 1 times. But if there's an error in the height, it's going to be twice of it. Understand? So that's what they're saying here. Therefore, when measuring terms which has been raised to some power, when we are measuring terms which has raised to some power, this is a power. When it's raised to some power, additional care should be taken. Additional care should be. So when we are measuring these things with powers, think twice. Okay, what you have to do is you have to use something which has a lesser discount. Understand? So to measure height, you can use a vernier caliper, but if it's raised to a power, you should think twice. So will this affect or something? So I will teach it later. So the error is going to be twice. Understand? So the percentage error is going to double. So if it's 1% for height, if you're going to use the exact instrument here, that 1% is going to be 2%. Understand? So in this meter ruler, it's going to be 100 millimeters, right? So if that 100 millimeter is going to be multiplied by 2, it's going to be 200 millimeters. So this height should be more than 200 millimeters. More than 200 millimeters. So if it is less than 200 millimeters, let's take it is 150. That means 15 centimeters. You can't measure it. But if the length is 15 centimeters, you can measure it. But it is greater than 100. Understand? I just explained it. I didn't briefly explain it. Think about it. Okay? That much care should be taken. So there will be questions from these sort of type questions. Understand? Okay? Right. When we calculate a final, the second pair of those, that same point, when we calculate a final result like y equal a to the power nb, the error of the quantity a will have greater effect on y, greater effect on the error in y. So let's take an area. Let's take an area. It's going to be length into breadth. So can you find an error? Can you measure area with an instrument? Any instrument? Can you find the area directly? No. You should find the length, breadth, and then we have to calculate the area. So the area doesn't have an error itself, but due to the error that is present in this length and breadth, there's going to be an error in the area. So if we are going to find the volume, it's going to be h squared into L. So the error from this, so both of these is going to affect for this area's error. So here the error from the height is much higher than the error from the length. Understand? So that's what they are saying. Same thing. We'll have a greater form. Therefore, we have to take extra care in measuring terms raised to powers. They have mentioned it twice. Okay, this is the exact point that I copy pasted from the resource book. Okay, I also saw that they are telling the same thing again and again. There was one page, and again in the next page they are continuing. I thought why they are saying it repeatedly, so there should be something there. They copy pasted it again. So they are mentioning it twice, so you should have to take it much. You should care it much than other stuffs when you have a power. So the next point, various measuring instruments are used to measure various physical quantities, but here we consider only measuring instrument used to measure physical quantities such as length, mass, and time. And in the first unit, we are using measuring instrument which we are going to measure the physical quantities which has a mass, length, and a time. So length, we use meter ruler, blah 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 blah. Okay, so as an additional knowledge, I have given you in page number, turn to page number 8, 9, and 10. Go to page number 8. Those letters are utilized, right? So I'm not going to teach them. Okay, that's for your additional knowledge. You can read it and take a knowledge. Here, I'll just introduce you all to this page, measuring instruments. Okay, this is where the measuring instrument starts. Until now, we were talking about errors and least counts. Okay, here in the measuring instrument, they are explaining what is a measuring instrument, blah blah, and there's a table. They have given you are going to measure length by meter ruler, vernier caliper, micrometer, screw gauge, spherometer, and traveling microscope. Okay, mass you are going to use double beam bass, triple beam bass, 4-beam, uh, balance, electronic balance, chemical balance, and spring balance. There are a lot of types, lot of ways to measure mass. Okay, so if you go to time, you have stopwatch, wristwatch, and stop clock. Okay, so temperature, current, potential, and resistance and volume. Those are not related to the first, right? They have mentioned here. Various measuring instruments are used, but here in the sense in the first unit, we are going to use only length, mass, and time. So highlight them. Length, mass, and time. So other are some extra knowledge for your other practicals. A measuring instrument, the last point in page number 5, come to page number 5 again. A measuring instrument has a scale and there is a least count which can be obtained from that scale. A measuring instrument has a scale and there is a least count which can be obtained from that scale. Okay, you can obtain the least count from the scale itself. The instrument is not used to measure more accurate values than this least count. So instrument is not accurate to measure something lesser than the least count. That's so obvious, because if the least count is 1 millimeters, you can't measure something less than 1 millimeters from the meter ruler, right? Okay, that's not 1%, that's 0.01%, 0.1%. Yeah, 0.01%. Understand? Okay, you can't measure anything less than the least count. That's really obvious. Okay, right. Uh, As an example, a meter ruler is calibrated in millimeter scales. The least count is 1 millimeter. Because of this, we cannot obtain an accuracy more than 1 millimeter. We can't obtain an accuracy more than 1 millimeters from a meter ruler. Okay, it's accurate to the first millimeter. So when you're writing readings from a meter ruler, let's take something 250 millimeters. So this is going to be, can you measure this sort of reading from a meter? Possible. Have a meter ruler, you're going to measure the length. Can you? Right? Too large. What? So in a meter ruler, we have only 1 meter, right? It's going to be how many millimeters? 1000. So we can measure up to 1000, but can measure this length. So yeah, going to use it twice, but it's accurate, right? You can measure. What's the condition? You should measure lengths larger than 100 centimeters, 100 millimeters. So it's larger than 100 millimeters. So it's going to be that much accurate when you're going to measure large stuffs. The error is only when you are going to keep one ruler and going to keep again the ruler. There can be some personal errors like keeping the away. Understand? But there's no any what errors. Object system at no random errors. There's no any random error. So let's assume we are going to measure 999. We have the reading 999. So if you are going to the best example 900, okay, 900 millimeter. So in this question they are saying, right, they are giving a picture of a meter ruler, and they are giving like this some object like this, and it is here, and this is the 1 meter. They have mentioned this is 1000 millimeters. They are asking, this is object, right? This is object, this is 8, and here, okay, they are asking what's the length of this object. You have been right, 900 millimeters. 900 millimeters ne? Sorry, 999 ne? Sorry. It's going to be is 900. 90 centimeters. Okay, 90 centimeters. So they are telling you to write this in what? In meters. Sorry, in centimeters. So you're going to write, how are you going to write this? You're going to write this 90 centimeters. Is this correct? Whenever you are going to take a reading, a level syllabus, practicals, you have to practice yourself to write that to the decimal place which you can find the least count. So the least count is how much centimeters? 0.1 centimeters. 1 millimeters. 1 millimeters means 0.1 centimeter. So unless it can be 0. Here you have nothing, but there's a 0. There's a 0. You should mention that 0 when you are writing this. Correct. So you should mention that there is no any least count here, no any millimeters here. Understand? So every time when you are going to take a reading and mention it in the answers as the answer in your practicals, you have to mention until the least count. That's what they are saying. Because of this, we cannot obtain accuracy more than this. According to this, we can express a measurement such as 16.3, 16.4, but not as 16.15. So only like this, you have 90. You can't write this as 90. You should put 0 and like this. But because the least count is 0.1 centimeters, you can't write it as 0.15 or something. Let's take, you have a measurement of 0.15 centimeters. Okay, you have something which has a length of 100.15 centimeters. Okay, not 100. Let's take it as 90. 90.15 centimeters. Okay, they have mentioned in the object it is 90.15 centimeters. It's 90.15 centimeters, but if after you measured it from a meter ruler, the least count should be 0.1. So you should write it as after you measure it, it would be something like this and that, but you can't write it as 15. You can write this as 90.1 or 90.2. Understand? Okay, right? This you can write like this because the least count is up to this decimal point, not this. Okay, right? All the important points are covered. Have any important points? No. Now we are going to error estimation. So before going to error estimation, I'm going to give you go to page number 10. Okay, few principles. So let's complete that note and go on. So in the bottom part of the page number 10, online students, the last part of the page number 10, you have the topic vernier and screw principles. Okay, this is the two types of principles. There are special measuring instrument. You have some points there. A meter ruler cannot be used for many measurements because it can only measure lengths with a accuracy up to 1 millimeter. Okay, there are special measuring instruments which have been used in such instances. They have two principles used in these instruments. So you can't measure anything which is less than 1 millimeter. So to find something less than 1 millimeter, you have to use instrument which have a vernier principle or a screw principle. So you have 2 points. I have given you dotted lines. Fill it as the screw principle and the second one as the vernier principle. The screw principle, the vernier principle. You can change it. That's fine. You can write vernier up and the next one here. Principle. The last page. So we completed the page number 11 also. Ne? Yeah, okay. Now we are going to page number 12. We'll do the error estimation part a little bit later. Been writing. Let's go to the least count definition. We had least count before, but I'm going to write it again. To make the first division of the vernier scale, write the note or the least count part. To make the first division of the vernier scale coincide with the first division. Wait, the vernier must move. All right. Is the definition for least count vernier in instruments which use vernier principle. At first, I gave the least count for every instrument which doesn't have a vernier principle and all the other measuring instruments. Let it be a clock, stop clock, measuring a beam, 4-beam balance, electronic balance. I gave least count to every common instrument. So now I'm giving the least count for the vernier instrument which have vernier principle. Okay, so start write it. The least count of a vernier caliper. To make the first division of the vernier scale, coincide with the first division of the main scale. With the first division of the main scale. To make the first division of the vernier scale coincide with the first division of the main scale, comma, the vernier must be moved. The vernier must be moved forward by a small distance. Vernier must be moved forward by a small distance. Equal to the difference between to make the first division of the vernier scale coincide with the first division of the main scale, comma, the vernier must be moved forward by a small distance equal to the difference between one vernier division and one vernier division and one main scale division. So, one vernier division and one main scale division. Full stop. Continue to the same sentence, same paragraph. This distance is known as. Okay, where did you miss? Which word? equal to the difference between one vernier division. Oi, okay, okay, okay. Shall I read it from the beginning? One vernier division and one main scale division. Between one vernier division and one main scale division. This distance is known as the this distance is known as the least count of the vernier scale. Distance is known as the least count of the vernier scale. Least count of the vernier scale. Okay, understood? Read it again and understand that sentence. So that's what a least count is. Least count is the length between one main scale division and one vernier scale division. You lost your. Okay, go to page number 12. Okay, you have a space after this. According to this list in page number 12, come to page number 12. According to this least count of the above vernier, according to this least count of the above vernier scale can be found. Okay, after that you have a space there. So copy this down. Length of one part of main scale equal to 1 millimeter in a vernier caliper. Length of one part of vernier scale equals to 1 millimeter to 9 divided by 10. 0.9. Least count equal to 1 part of main scale subtract 1 part of so this is equal to 1 millimeter subtract 9 millimeter. So 0.1 millimeter. Why don't you want to be cool, right? The next day I'll tell Pali to remove these tables. So you all don't sit any? Girls sit here. Here no boys. Girls no. The boys start to sit here, girls start to sit here. So I'll remove these tables here. So I can here. That's fine with me because I'm your generation. But I was a front. There are like students are categorized into sort of types. Front benches, they have to see the actions of the lecture or something sort of thing. The ones who sit in the last bench, they have the hearing ability more than the ones who are in the front bench. So the front bench students need to look, have to hear. Last bench students, they don't look, can hear. By only hearing, they have the ability to write the note. I mean, last bench, others who is just dancing and unnecessary stuffs. One student from all coming to my next class doesn't look at really like really hard to teach and he's not looking. I think he's like doing something else, but he's looking at his note, talking with his friends, but his note is complete. He do every his yeah he's a good student, right student. So I don't worry where you sit. You can write the note. You do the error shell. That's all I need. Okay. So you have another part. There is another method to find the least count. So there's another method to find the least count. So we are going to find them. We are going to find that. So how did we find the least count? 1 millimeters subtract 0.9. How did I take 0.9? 0.1 multiply by 9 divided by 10. Okay. This that have to come. Okay, you have the have number of verniers and value of addition for main scale, value of addition. Can do it. like this. So part of a main. Here you are finding value of a division of the Vernier scale. Okay, first we are using this part. B. What's B? I have given you a small description, but I have given you some algebraic terms N, A, and B. I'm going to use those parts. Value of a division in Vernier scale. Vernier scale. Cool up. Going to reduce the temperature. Come here. Value of a division in the Vernier scale. Value of a division in the Vernier scale. That's 0.9. Okay. I'm going to multiply that by number of Vernier scale divisions. How many? How many Vernier scale divisions have? 10. Okay. 10. And I'm going to equalize that. I'm going to equalize that to value of a division in main scale. What's it? Its value of a division in main scale is going to be 1 millimeter. Okay, so you all know that 0 and 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the 10 of the Vernier scale is here. This is Vernier and this is main, right? So 10 is here. This is going to be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So this one here, I'll divide it to 1, 2, 3, 4, 1, 2, 3, 4. Okay, so this is the Vernier. So here the 0 of the Vernier is coincided with the 0 of the main scale, and 9th of the main scale is coincided with the 10th of the Vernier scale. Okay, 0 with the 0, 9 with the 10. So I'm going to use this feature of this Vernier caliper here. What I'm going to equalize value of a division of a Vernier scale. Vernier scale is 1 division multiplied by 10 should be equal to how much of Vernier scale? 9 of Vernier, 9 of the main scale. 9 of the main scale. So value of a division in the main scale should be multiplied by 9. So if 10 is equals to n, 9 is equals to n what? N minus 1. So I'm going to write here n minus 1. Fine. Okay, right? Okay, so this is equal to a, and this is n minus 1. This is equal to b, and this is n. Okay, which is equal to b and n here. I'm going to subject b. So here I'm going to have a n minus a over n over n. I'm really lazy to write a lot of steps since I'm a max student. Okay, you'll understand this. Do you understand? Okay, okay. I'll go from. So what did I do? I kept this n minus 1 divided by. I was going to write this. I was just look right there. Okay, this. Can you understand this? After that, what I'm going to do? Now I'm going to multiply this a by this and this. An minus a. Okay. So this is a common denominator divided by n. Fine. So I'm going to give this n to both of this because this is the common denominator. I'm going to write this n here and this n here. Fine. Now an a here n belongs to both this. So n in the numerator, n in the denominator. You can say minus. We can't cut it like this. This is wrong. What did I do? I separated this into both of these sides. So now I can't cut this to this. If I cut like this, there's no denominator for him. But in here, you have a denominator. I expanded, and after that, I cancel it out. Understand? Okay? You should ask doubts, sir, if you can't understand. Okay? Did you understand? I said that from a minus, you have an infinity line. But you can't go because you have closed it from a bracket. So you have to divide this into 2. You can divide that. Okay? Understand? Right. That's all you have to manage. So the thing, you have to manage that space. You have to manage that. Not only this, you have another part also. Have another part. You don't write this. Don't write this. Don't write this. Right. Write on this. So okay. Develop the space. Have something. ඒ වගේම තව ටිකක් තියෙනවා. That space. Fine. Finished. So we manage the space. If not, what are we going to do? Cut off this. I have to write this. So don't write this. Copy down from here. And write this. Not equal to this. So now, what is the least count? What's the least count? Least count is count division of a main scale, that's A, division of a vernier scale, that's B. Understand? Okay. So you have space. What I'm going to do, I'm going to put A here and take B from here. So B is equal, here is equal to A minus A over N, right? Okay. I'm going to use that B. Okay. I'm going to use B here minus A minus A over N. Fine. So A negative positive negative A negative, here's a negative 1. I'm going to multiply that 1 by these 2. Okay, negative, positive, negative, 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 positive. Okay, a over n. Okay, fine. So a minus a is equal to 1 minus 1 minus 2, 3 minus 3, 0. A minus a. Okay, so the answer here is a over n. That's a over n. I know 10. 9 over a means, what's a? Value of division of a main scale. What's it? What's the value of a smallest division? 1 millimeter. Okay, n means the number of divisions in the n is 10. So 1 divided by 10, 0.1. Now, after I have taught this, do not find the least count by subtracting the main scale's division by the vernier scale's division. You have to do a lot of steps to find it. Okay, from now onwards, how are you going to find it? 1 millimeter. So every time in a vernier caliper, the main scale, the least count is only in the main scale, the smallest division is 1 millimeter. 1 millimeter. Some other cases there is some but mostly it's 1 millimeter. So because we can't read less than 1 millimeter. Sometimes there may be some small points less than 1 millimeter is going to be 0.5. Okay, some vernier calipers mostly it's 1 millimeter in the main scale. The smallest division in the main scale is 1 millimeter, but in some rare cases there can be they can mark 0.5 millimeters also the main scale. Okay, so what's the smallest division? Mostly it's 1 millimeter. So the numerator is not going to change ever again. Smallest division in main scale a 1 millimeter. So this is what that's going to change. If they are going to give a vernier caliper, count the divisions in the vernier scale. Mostly they are going to give it. They are going to give in the vernier caliper, you have the main scale, you have the vernier scale. So they are going to mark like this and mention at the last point. That means it has 10 divisions. Okay, substitute that 10 here. This is mostly 1. So that's going to be answer. Okay, for that I'll give you a small example. Go to page number 11 to explain your. So you didn't write me this part? Don't write, wait, don't. So to explain your will. So in the 11th page, you have a diagram like this, a part like this. Okay, this is the main scale. They have inverted it. This is the vernier scale. So how many divisions do you have here? Have marked like this, like this. How many divisions? Count them. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not here. The diagram. The diagram. How many divisions? 10. Here 10. So the least count. How are you going to find the least count? LC. So I'm going to use LC from here. Least count. That's going to be the smallest division in main scale. I don't know that. I didn't read that. So how many divisions are there in the main scale? 10. Okay, 10. So the numerator is A. A means the smallest division in main scale. So the main scale is here. The main scale is here. So there are like this stuff. So the smallest division in main scale is the length between these two. That's it. Read it. So they have mentioned that this is 10 millimeters. 10 millimeters. This is 5. So 1. How many millimeters? 1 millimeters. Understand? Okay. Right? 1 millimeter. So this is going to be 1 millimeter. So the answer is going to be 1 divided by 10, 0.1 millimeter. So another example. So I don't give you examples mostly. Irritated. Go to page number 16. Go to page number 16. very special, very rare case. Okay, this instrument. So I said that I didn't say that. So I'm going to say that now. You have four instruments: vernier caliper, traveling microscope, micrometer, screw gauge, barometer. Okay, let's go to vernier caliper. Vernier caliper, you have two vernier calipers. One is the normal vernier caliper. I'll write it normal. The next one is a very rare special case where students get confused. It's known as the extended vernier caliper. Extended vernier caliper. Extended vernier caliper. Whatever the vernier caliper, it is a vernier caliper. If it follows a vernier principle, how are you going to find the least count? Smallest division in main scale divided by the number of vernier divisions. Okay, this is a really confusable area. Okay, right. So in this figure, in page number 16, the figure they have given is an extended vernier scale. Anybody, can anybody find the difference between the normal and the extended part? Just look into that vernier scale. See what's the difference. Tell me one difference. You difference. So the lower part here is the vernier scale. For now, you can mention it in page number 16. In page number 16. Page number 16. Sorry, white color. Page number 16. Page number 16. P16. Right, student. Page number 16. Have a diagram like this. Here you have 4. You have 10 here. Here you have 4. Here 0, 0. So this mentioned here from your blue or black pen is the vernier scale. This is the main scale. Okay, main scale. Right. So what's the difference? So I taught about vernier calipers. Where does this coincide? How many division of the main scale? How many millimeters? Tell me. So write this additional part also. Is 4 centimeters. 4 centimeters. Okay, that's 4 centimeters. Right. The 10th division in the vernier scale has coincided with the 3.9 or 39th millimeter scale. Okay, so usually it coincided with the 9th one. Okay, but here it's 39. So the first point is it coincided with the 39th. So meaning of extended would be this, because it's extended. So 9, now it's 39. First reason. Can anybody find a second reason? Look clearly vernier scale. One lambda. Lambda here. Which value? 39. No, that 10th one is aligned with the 39th one. We have supervision. No, they're not correct. oh, this is not clear. It is not clear. I took it from the resource book. In the resource book, it's not clear. Okay, but no any other points coincide here. That's a rule in vernier calipers. In vernier scale, when 0 and 10th are aligned, not only 10th, when 0 is aligned, 10th is aligned, but no any other one is aligned here. Okay, so if you saw something aligned, that's not aligned. Huh? That's not aligned. That's because of the unclearness and the vision of yours. So the next thing here is count the number of divisions in the vernier scale. That's it. That's it. How many divisions do you have in the vernier scale? Ahead? Huh? 20. Then you have 20 divisions. But normally you had how many divisions? 10. So you have 20 divisions in the vernier scale. 20 divisions in the vernier scale. So these are the 2 points and extended vernier caliper. Okay. So right in the example I have given you under the extended vernier caliper part, a vernier scale in which the marking are not closely placed to facilitate reading. Okay. So this is a vernier scale in which the marking are not closely placed to facilitate reading. The vernier has 20 divisions. So it's an additional part. It requires time to explain it. So I'll okay. Look here. So what I want to do, I want to measure something much more accurate than using a vernier caliper. So the least count is 0.1. To measure something more accurate than a vernier caliper, the least count of that instrument should be less than 0.1. Okay. So if there's an instrument lesser than 0.1, it's much accurate than vernier caliper. So I have to decrease this, the least count. So I'm going to the formula of the least count. Least count is made by what? The main scales division and number of divisions. Okay. Main scales, smallest divisions length and number of divisions. So least count is proportional to the main scale's smallest division. Okay, I'll mention a small. How to mention? However, this is main scale smallest division. Okay, if you all need, I can write in. No, this main scale smallest division directly proportional to main scale smallest division. Just give time. Okay, 10 o'clock. I know it. Least count is again inversely proportional to what's 10? Number of vernier scale division over what? Okay, number of vernier scale divisions. Understand? So we have to reduce this least count is directly proportional. So we have to reduce what? The length of the smallest main scale division. So what should I do? It's 1 millimeters. So I can reduce it. So I can mention a scale between 1 millimeter and make it as 0.5 millimeters. I can do that. It's easier. But the thing is, it's hard to figure it out because you are going to have many scales in main scale division. Understand? So it's hard to figure it out, but we can manage it. Okay, we can figure like 1 millimeter is like small part. If there's a small dot between this, can you recognize it? Possible. Just take a rule and see it. Take a rule. There's a line between 2 millimeters. Can you figure it out? It's easy. Yeah. That's much easier than dividing 1 millimeter into 10 parts. If you divide 1 millimeter into 10 parts and if you are going to figure it 0.1 millimeters, it's hard. But more than that, you can see a point between 1 millimeter, between 0 and 1 millimeters. So what I'm going to do is I'm going to decrease the main scale's smallest division into 0.1. 0. What 0.5. Okay, I can do like that also. So what I can do is to decrease these counts, since this is inversely proportional. The thing of inversely proportional is to decrease this, I have to decrease the directly proportional, inversely proportional, I have to increase this. So when I'm going to increase the number of vernier scale divisions, the least count is going to, okay. Now what I'm going to do, I'm going to increase the number of divisions in the vernier scale. So that from 10, I'm going to move on to 20 vernier scale divisions. But the thing is, normally one division between one division, what's the length in a vernier scale? It's going to be 0.9. 0.9. So between 1 millimeter, if we keep a dot in the, if you divide 1 millimeter, this is 1 millimeter, we are going to keep a scale between this, that's going to be 0.5. 0.5. It's hardly recognizable. But if we are going to make this half, it's much harder to recognize a point between 0.9. More than this, it's much harder because this is 0.9. We are going to make it half means it's going to be 0.45. It's much harder. So what I'm going to do is I'm going to make this longer. There's no any rule that one division in a vernier scale should be 0.9. There's no rule. So what I'm going to do is I'm going to increase the length. Okay, I'm going to double this. I'm going to double this and make this 1.8 and mention 1 in this. So this is 0.9, but this is what's this? This is totally is 1.8. Okay, and what I'm going to do now is, instead of decreasing the main scale division, I'm going to increase the number of which the vernier scale is going to coincide with the number of main scale. Understand? So that I moved from 9 to 39, and I moved from 10 to 20. Okay, hardly describable, hard to teach how to extended vernier scale working, but I tried and I did my best. Nobody's going to explain extended vernier scale. It's very hard to think about it. Okay, explain vernier scale is much harder. If it's going to be an extended vernier scale, it's much more harder. Now what I'm going to do is, so now since we did some changes, we did these changes, why we can't mark 0.5, okay, millimeters. Okay, we can't mark it because if it's harder. So it's harder to find which one is going to coincide with which vernier scale, because I said if this is 0 of the vernier and 0 of the main scale, if this is 1 and this is the 1 of the vernier scale, main scale, so there's a small gap. Okay, now since we are dividing this to 2 and we are going to divide this to 2, this distance between this is going to be half of this distance. Okay, we are dividing this to 2. This is 1, this is 1, this is 1 of this is 1 first of vernier scale, this is first of main scale. If you are going to divide this to 2 and divide this to 2 to coincide this, the length here, let's take it as L, this should be 2L. Okay, so this is the least count, that is 0.1. This is 0.05, half of this. This is 0.1. Okay, this is going to be 0.1's half. So if you take it as 10, half of 10 is 5. So what I'm going to do is I'm going to erase this 10 and put a 5 here by putting 0 here. How we divide it? Okay, understand? Okay, so this is 0.5, this is 0.1. So looking at here, coinciding, this is much harder. Like if make one vernier scale aligned with a one main scale, it's really hard to watch which is coinciding with this. But there's a trick. Okay, there's a trick to find it. But if this gap is going to decrease much more, it's much harder than this to coincide to look which one is aligning with which. Okay, that reason what they are doing, they are going to increase the number of divisions that's coinciding with the division of vernier scale. That's why they have invented extended vernier caliper. To go to page number, we were reading, yeah, we reading some points. Where is it? something. That point. It's I start to explain this. After explaining this, I said not to write this. I move on to this, and I read statement. And right, this statement. Come to this. In page number 16. In page number 16 itself, after the extended vernier scale part, you have in the example the first sentence, a vernier scale in which the marking are not closely placed to facilitate the reading. Not closely placed to facilitate reading. So that's why they have extended it. The reason to extend the vernier caliper is to reduce the least count, and if we reduce the least count, it's hard to read, so that they have extended it. Understand? Okay, right. So that's why extended vernier caliper is made. So we'll come to the extended vernier scales note. So before that, you should write this, and before that, what you have to take a break. Take a break and start to write this part, or write this part and take a break, whatever you do. However, after the break, I'm not giving time to write this. I'll give like 5 minutes to write this, but it's your choice. It's much better to write this note. You have to write from here to here. Light blue. So today I'm going to give only 10 minutes break. Because 10 minutes. 10 minutes. Now 15 minutes. So you have to come here. It's 15, 10, 15, come here 10, 20. Okay. Especially 3 girls. Okay. You 3 girls take a lot of time. So I'm going to start at we are going to come at 10:30. Then I'm going to give every time 15. If not, if I tell you to come at take a minutes of 10 minutes break, you will come surely at after taking 15 minutes break. That's why I'm telling you to take minutes break. If I tell you to take 15 minutes break, you are going to take 20. Okay. This time you should be much accurate. Come at 10:30, 15 minutes. Should be at 10:30. Yeah. So don't worry. The ones who didn't come to the class, I have the recording today. Okay. Online students, can you hear me? Online student, take a screenshot of this code. Take a screenshot, and if you want, you can have to write this part. You'll finish writing it. Wake up, wake up. A headache or something. Sleepy. Okay. So now we finished what least counts, shortest method to find at least count. Now let's move on to extended vernier scale. So did you manage your space? This one. Manage space. Okay. So you have small box there. Least count is equals to least count is equal to what? A divided by n. Okay. Don't write that. Don't be lazy people. Write the long elongated form. But A in the sense value of a division of a main scale. Value of smallest division main scale in main scale divided by n in the sense number of vernier scale divisions. Number of vernier scale divisions. Number of vernier scale divisions. Right. Okay. So let's move on to extended vernier scale. So I hope we can go to the right. You'll know what an extended vernier scale is. Okay. So page number 16. Page number 16. We are moving here and there in the tube. Okay, don't worry. Finally, I'm going to complete it. Okay. So a vernier scale in which the marking are not closely placed to facilitate reading. That's the extended vernier scale. The vernier has 20 divisions. It has 20 divisions. It has 20 divisions. 20 divisions. And equivalent to a length of 39 millimeters, equal to a length of 39 millimeters on the main scale. What's the shortest measurement that can be read from this instrument? So we are going to do the longest form to find the least count. The shortest length in the sense that's the least count. That's the definition of the least count. The shortest length that can be measured from an instrument. That's the least count. So we are going to find it by the longest form and the shortest form as well. So there's a small space. So let's start to do it. Okay. Right. So as we did it for the the normal vernier caliper, we are going to write it. So least count is the smallest measurement. So we are going to find least count is equal to, this is a little bit different. If you are going to find this in the longest form, extended vernier calipers least count. To the method find the least count of extended vernier caliper in the elongated form is a little bit different. So first of all, how did we find the least count for normal vernier calipers? Main scale division, main scale, length, subtract vernier scale, length. Is it length? Length of one division, right? Understand? We subtract this from this. So we got 0.1. Okay. But here, just go and look at the diagram. Go and look at the diagram. See one scale, the first scale of the main scale. Go to the main scale. Just look at the first scale. You have the 0th division and the first scale. Okay. And go to the 0th scale of the vernier caliper and the first scale of the vernier caliper. Can you see the difference? Here, first of all, in normal vernier calipers, the main scale was the one division of a main scale is larger than one division of a vernier scale. But here, one division of vernier scale is larger than, here in this place, one division of vernier scale is larger than one division of main scale. Did you understand that? But we can't subtract one division of vernier scale from one division of main scale to find the smallest difference. So what we have to do is we have to find the first of all find the first division of the vernier scale. Did you find it? You have the 0 here, you have a 0, and you have the first, the vernier scale. Okay, so in this first scale, look here and there over this first vernier scale in the main scale. Can you see any division that's going to coincide with it? And you see a main scale division which is closer to this first scale. Which one? How many scale of the main division? Second scale. Look closer into the diagram. Okay, that's the second vernier scale. So to see the lowest least count, we have to move this vernier sliding part to align with the second scale of the main scale with the first scale of the vernier scale. But second scale of the main scale to coincide with the vernier scales first. Understand? Then that's the least count. So this least count is less than 0.1 millimeters. That's why we use a extended vernier scale. Understand? So this is most probably 0.05. Okay. From a vernier caliper, we can go maximum up to 0.05. We can't go more than that. If we are going to more than that, we are going to face a lot of problems. Main problem, printing. We can't print more than little bit lines. It's hard to print them. Okay, so we can print more than that using nanotechnology. For example, if we are to manufacture chips, I mean not chips, microchips. I can remember. Huh? Semiconductor, in the sense you make transistors from diodes, make a transistors, a lot of transistors, and make a processor. You all know the processor in laptops and computers, the i7, i9, like that stuff. You have a main core there. In there, they manufacture this with nanoscale difference, angstrom difference. Angstrom in the sense it's going to be lengths between atoms. That much scale they can manufacture particles. But to measure something much accurately, we don't want to do that. The largest industry in this world is industries which manufacture chips, microchips. Okay, so why should we make a vernier caliper by that big large industry? So these sort of industries are very rare. Mostly there are only 3 industries which manufacture processors: Apple, Intel, and RMD. Okay, so only 3. Then you can see this is a big world. Only 3 industries. Mostly, I for now I have only knowledge about 3, but I don't know. There can be more. But mostly it's really rare. So if you take A water bottle, there are a lot of companies which manufacture water because it's easy. So with the hardness, the industry number of industries get reduced. So to manufacture vernier caliper, we don't want to go to a nano scales, right? So with the ability to make a vernier caliper with the lowest cost, we can go only up to 0.05, right? This, but extended vernier caliper, and in a normal vernier caliper we can go up to only 0.1. Okay, this is an extended vernier caliper, and let's look into that. So to go more than this deeply, we can't, the vernier caliper is going to be limited. Vernier principle is going to be limited up to this. So to go more than that, to measure the thickness of a paper and those like stuffs, we use the screw principle. That's why the scientist introduced the screw principle. Okay, now let's move on to that. So before that, what I'm going to do is, now I found that the first scale of the vernier the first scale of the vernier scale is much closer to the second scale of the main scale. Second division of the main scale, sorry. First division of the vernier scale is much closer to the second division of the main scale. So what I'm going to do is, rather than subtracting, since the one vernier division is greater than one main scale division, rather than subtracting main scale from the vernier scale, one main scale from one vernier scale, what I'm going to do is, I'm going to subtract two divisions in main scale from one division of vernier scale. Understand? Okay, one vernier division is greater than one division of the main scale. Okay, that's another difference. Okay, I have to mention that. The next difference is, the third difference is, one division in vernier scale is greater than one division in main scale. So these are not really important, the A levels, I mean not the final paper, but you have to know a basic knowledge to this deeply. So that's why I'm explaining this stuff. Let's say one division of vernier scale is greater than one division of main scale, because I had all of these doubts. Okay, I had that much doubt. One of my friend messed up with this vernier caliper. To, like, at the final exam also, he was using the elongated form to find the least count. So you don't want to do that. But the magic here is, in extended vernier caliper, the longest form is different, but the shortest form is exactly as the normal vernier caliper. Okay, let's try it. Okay, so what I'm going to do, I'm going to, did I select erase, right? Okay, really fun, right? Okay, this is going to be equal to what? Not two vernier divisions. This is going to be not one. This is going to be two vernier divisions. Two main scale divisions. Sorry, two main scale divisions. Subtract one vernier scale division. So two main scale division is going to be how much? What's the length? So I said the minimum we can measure here is from main scale is how much? Millimeter. We are not going to 0.5 millimeters in main scale. Why? I say the reason, because it will cause some errors. It's really hard to figure which one is coinciding with which. So that's why we still didn't go to 0.5. Still the smallest division of a main scale is going to be 1 millimeters in length. So two divisions in the sense, how many millimeters? 2 millimeters, right? So 2 millimeters subtract, this is millimeter. Okay, so how when you are going to approaching L, you are going to write millimeters like mm, because there's no time. Have to save time. Okay, so one vernier scale length of one vernier scale. How to find it? 49 or 50? That's 49, right? 49. 39. Sorry. 39. Sorry. 39. So 39 millimeters of main scale is coincided with how many vernier scale divisions? 20, right? 20. Okay. Do you need to multiply by something? No, just length of one vernier scale division. Understand? Understood? Online people, you don't have doubts, right? So what I'm going to do is, I'm going to find it out. So if you divide 39 from 20 for bio students, this is how you divide stuffs. So 39 divided by 20, right? How do you divide this? Easiest method, 39 divided by 20. Can you see this? Hmm? I'm going to make this 10 into 2. 39 first, I'm going to divide by 2. Okay, this is going to be like 30 divided by 2, 15. 9 divided by 2, 4.5. So 15 plus 4.5, 19.5. 19.5. Understand? 30 divided by 2, 15. 9 divided by 2, 4.5. Equate both. 19.5 divided by 10. It's going to be 19.195. Full stop. Not full stop, decimal. Okay. 1.95. Right? 1.95. Should be much great. Good if I can change the colors after writing. So 1.95 millimeters subtracted from 2.00 millimeters to be much clearer. So this is going to be how much? 200 minus 195? 5. So 200 minus 195, that's going to be 5. So before that I have zeros and I have a full stop. I mean decimal, it's going to be 0.05 millimeters. Did I come to that point? Yeah, 0.05 millimeters. Okay, now I can measure up to 0.05 millimeters. You can break the gem which is 0.1 millimeters with your dad's hand and measure it. Okay, now go to your home, take a gem if your father is doing a gem business. Mostly, how many fathers doing a gem business? Only one. Oh, that's one. Enough. So you're going to get treats on her birthday, right? Gems as gifts. Okay, oh, you have to copy this. Okay, start to write this from here. Right, students, can you see the blue color font? Okay, start right from here. Can you? Now see this. Yeah, sir. Yeah. Januka. What is the page number? Good question. Page number 16. You're listening to this without turning the page. Hmm? Page number 16. Okay. We'll take the identity card now. No. So I'm going to hack your brain taking the identity card number. I can't do anything. But like in 2020 or something, there was an app issued from the government. If we know the national ID card number, we can take the information in the ID card. But they here that app is there. That's a bit unofficial. They are used by some strictly official people. Only the details in the identity card number: gender, name, the full name, address, stuff. Okay. Small space. Okay. Please count is the smallest measurement. Have they asked from find the smallest measurement. They are going to find the smallest measurement. So what I'm going to explain them. I'm not going to find the smallest measurement, but I'm going to find the least count. But the least count is equal to the smallest measurement. So the next thing is you have to keep space to do this in the shortest method. It's a little bit tiny in a tiny font. Okay, I'll write it here. I'll use a yellow color. So least count as per our knowledge, is going to be A over N. People tell me what's A? What's A? I mean the definition, what's A? Just don't turn the pages, just what's A? Number of values. The numerator should be less than the denominator to get something like a decimal, okay? Division of 1, the length of one division of main scale. Length of one division of main scale. So what's it here? What's it? 1 millimeters. 1 millimeters. Right. What's in the denominator? Number of divisions in main scale. How many divisions do you have? 20. 20, right? Recognizable? 1 divided by 20. 1 divided by 2, 0.5. Divided by 10, 0.05. So this is going to be 0.05 millimeters. So, okay, right. I was searching something else. In the same page number 16. So here's a question from 2006 past paper. Okay. There's a lot more detail in this. So let me write this here. If n minus 1 number of main scale division of a third, I have mentioned certain, of a certain measuring instrument is divided into a vernier scale divisions. Is divided into vernier scale divisions. Full stop. Correct, comma. Then the least count of the instrument in the main scale division is the least count then the least count of the instrument in main scale division main scale division and 1 1 2 1 over 2 3 n over n minus 1 4 n minus 1 over n 5 1 over n minus 1 6 sixth option 75. You're writing it. Okay. So what would be the answer? If n minus 1 number of main scale division of a certain measuring instrument is divided into vernier scale division, then the least count of the instrument in main scale division is. Smart students, tell the answer and write the question. Smartest students, write the question and write it in a notebook if you want, but I don't recommend you to write this. Don't even write, because I'm not going to do questions. Tell me, what's it? So if the number of main scale division of a certain measuring instrument n minus 1, where did you that n minus 1? N minus 1. Value of a division in vernier scale n, value of a division in main scale into n minus 1. Take just a normal vernier caliper. So why did we mention n minus 1 here? Because of 9. The 9th division in the main scale coincided with the nth division in the vernier scale. Okay, understand? So what? So what's this n? I mean the definition. That's n. That is max, students. Go and read it. both of your max ne? What's it? N. Page number 12. Number of divisions in vernier scale. So there are n number of divisions in vernier scale. That's what they're mentioning. And what is this 1? What's the meaning of this? 1 millimeter. Then how did we get that 1? Vernier scale. Yeah, because there's only like if we go to the extended vernier caliper, because in the vernier caliper, when in a vernier caliper, the number of main scale, the coinciding number of vernier scale with the number of main scale is 1 less than the number of vernier scale. Okay, the normal vernier caliper, not in the extended. So in that case, you can go to the long form and find the answer. Okay, so you have n number of divisions, but n number of vernier scale divisions, and what's 1 here? 1 is the main scale's least count. Main scale is least count in the sense the smallest division in main scale. So what we are going to do, we are going to divide 1 by n. Okay, this is the least count of the vernier lever. Okay, understand? You copy this if you all want and mention it 2006. Question from 2006. An MCQ. Huge mistakes in old past papers. Because before 2012 or 11, 2012 or 11, they used to make the paper from Sinhala medium and then translate it to English medium. Okay, but now what they do is they make the paper from English medium and translate it to. That's much better. We are going to make the our professors are making the A-level paper, right? So professors learn from English. After A levels, you don't use Sinhala. What? You don't use a silly Sinhala word even. Whatever the thing you are going to study, that's going to be in English. But some professors or some lecturers, for the sake of students, they tell the English medium terms also. Okay, just if you have any English medium students or if Sinhala medium student or if your brothers and sisters is doing A level, hoping to do the A levels in Sinhala medium, tell them not to do because no point of that. In their now you should have an A-level knowledge, to the university stuff. So you can't do it. So before that, you should have a English knowledge. So in the development program, before they are starting our semesters, in the development program, they teach English. So we have 2 modules in English. We have 9 modules, modules in the sense subjects. We have 9 subjects in the first semester. 2 of them are English. For me, only there are only 7 subjects to learn. So, and it's much easier than other students. So I did a lot of extracurricular activities and I did the exams much easily. But other students, like, they went in hell. But most of the, so when coming to engineering, so they, however, they are a little bit electronic people. So they know to program, they use social media. So, however, now the newer generations are much uh, much with the phones, so they know English stuffs. But all in our batch, in the sense from our batch only, it's changed because we are the batch who were influenced by the coronavirus in all levels. So after that, we got phones and we are dealing with phones, and so our batch people are a little bit familiar with English. So your people are also a little bit familiar in English, but they are still studying Sinhala. So Skandaya, you know what is Skandaya? Oh no, Skandaya. Who knows Skandaya? Bara? What's Bharat? I was like mad. I don't know Sinhala on those times. Not like you people. You are Sinhala Buddhist. I am Muslim, so I don't know a lot of Sinhala words. But still, I went to Sinhala classes and learnt A level in English medium. Okay, I can't remember now, but I learned physics, like half of physics in Sinhala because they were not teachers. Okay, right. So this is going to be 1 over 9, 1 over n. So let's move on to other parts. So let me check your book. The extended vernier caliper is completed. Vernier caliper, we have to go to the readings. We can do some examples. Have to do the estimation. So the best part is before doing the examples, easy. Shall I finish those examples? It's a little bit interesting and come to page number 30. Let's finish it. It's much easy. It's much easy. So there are different types of verniers. They have given different types of vernier calipers as questions. So first example in page number 13, 1 3. All right, students. Would you mind adjust a little? What is the page? Would you mind adjusting board little? By that. Rabesh. Oh. Hi, hi. So do I need to adjust the board? I mean, I have to remove this and do that. I have to adjust the camera, I guess. Okay, fine, fine. I think that's okay now. Go to the example number 1. That's not me. Yeah, yeah, I know that. Cannot see the whole board. Is it? The two people in online is arguing, right? Yanuka is telling that he can see the board. You can't. Is it? He's lying. What's the spelling for lying? I, E, G. Then Y. ING. Then the continuous tense for lying down. That's the same thing. No, it can't be. Is it? No, no, right. Rabesha, can you see the board or not? I have to confirm that because I did some settings here. Any coverage problem? Or I don't know. Shall I continue then? Who knows Prabesha here? You know this girl. You were not in the yesterday's class and before yesterday's class. I can say, okay. You're making me mad, right? Okay, let's go to the example number 1. In page number 13, again I'm mentioning it, go to page number 13, okay? In the practical tute, not in other tutes. So the first example, what are they saying? They're saying main scale of a vernier caliper is marked in 1 millimeter divisions. So what's the smallest scale, the length of smallest scale in main division? 1 millimeters. Length of 10 vernier division is equal to a main scale division. Okay, 10 length of 10 vernier scale division is equal to give me a minute. That there's a main scale, that a should be 9. Okay, that a should be 9. What? Length of 10 vernier divisions is equals to 9 main scale, not a main scale. That's 9. I don't know how these guys confuse A and 9 in the keyboard. When you are writing, A and 9 is a little bit different. It's equal, right? But in the keyboard, that's not. I don't know. I think this is a written one and then translated into something. I borrowed this question. That's why. Okay. So 9 scale divisions. Find the least count of this instrument. So I have given the steps. What's the first? What you have to find is the long form. Length of one main scale division. Length of one main scale division. Let's move here. Division. That's going to be equal to how much? 1 millimeter. Roman number 2. Length of 10 vernier scale divisions. Length of 10 vernier scale divisions. So we have to mention that also in millimeters. How much? How many millimeters? 9 millimeters. After that, length of one vernier scale division. So this is step-by-step guidance to find the least count. Length of one vernier scale division. Going to be 1 divided by 9. Students, what's it? My goodness. I can tell that's 0.1 without doing a calculation. Huh? You should write it, right? 1 millimeter. Okay, 1 millimeter. Tell me, 1 millimeter. Sense? You want to kill somebody. Subtract. What? What's it? What? Of 1 vernier scale division. How are you going to find it? Length of ones. Am I wrong? Okay. 9 divided by 10, not 100. 10 millimeter. Okay. It's going to be 0.1 millimeter. You have to write this. If not, I am not giving this much space. After that, least count. Write it aside. And finally, the fourth step. Lazy people. Least count is equal to my goodness. Sir. I'm not wrong. 9 millimeters divided by 10. I was not wrong. Did I do any mistake? No. It's 0.9. 0.9. You should tell, right? Just tell me. It's going to be 0.1 millimeter. Did you find this mistake? Did you? But she was the only one girl who was arguing that. Correct? No, it's okay? Okay. Who said 0.1? Length of one is? Nobody. That's the least count. So next you have main scale. Let's move on. Soon. Ready? So next we have main scale of a vernier. The main scale of a vernier caliper is marked in 1 millimeter divisions. So again, the length of one main scale division is going to be 1 millimeters. After that, length of 50 vernier scales. 50 vernier scales is equals to 49 divisions in the main scale. So this is the main scale. This is the vernier scale. All right. Find the least count of the vernier caliper. So length of 10 vernier scale divisions. That's going to be what? Length of 10 vernier scale division is going to be, oh no, it should be 50. 50 vernier scale division. Now 50 is aligned with 49. So length of 50 vernier scale division is going to be 49. People understand? Right. This is a different type of vernier scale. I said there are different types of vernier caliper. The first, in the example one, that's the standard one. Okay. Now let's see what's here. It has 50 divisions. Vernier division is equal to 49 divisions in the main scale. Find the least count of the vernier caliper. So length of one vernier scale division is equal to 49 divided by 50. Okay. No. Okay. Right. So that is going to be 0.98. Sure. Damn sure. Use the calculator. No. You have the phone, right? You can multiply both by 2. It's going to be 98. So 0.98. Understand? So least count is going to be least count is going to be 1 minus 0.98. We didn't write the step earlier. Is going to be 0.02. Right. Any doubts? Understandings? The tiny value? No, no, no. This is correct. This is correct. There can be doubts. Okay. Right. So 0.02. Right. So in extended vernier scale, what was it? 0.0? 0.05. In an extended vernier scale, we found it. It was 0.05. But this is much less than that. So the least count is much lesser than that. So we can use this. Why didn't you use? So not a vernier. This is not an extended vernier scale. Okay. Why? They have said that 49 with 50. If it's a vernier scale, then they are mentioning here it's extended. So from the data itself, we can tell this is not a vernier extended vernier scale. But the thing here is 50 is coinciding. Sorry, 49th one is coinciding with 50. Then think what would be the least count is 0.02 millimeters. Then it would be much easier to align two lines, much harder than aligning an extended vernier caliper. Is 0.02. So gap between, once you take your finger and start sliding, it's going to jump. You can't make your finger that much smooth to do a fine adjustment. Okay, you have to jump 0.02 millimeters. Really hard. It's 1/100 of a millimeter. 1/100 multiplied by 2. Understand? So this is a little bit ideal. Ideal in the sense it's really hard to make these sort of vernier calipers as well as to measurements from this side of vernier calipers. We should, let's say they have made some vernier calipers like this. So if we have to use these sort of vernier calipers, we should use a magnifying glass. Understand? So to see if they are aligning. Understand? So in a traveling microscope, they have given a magnifying glass by default. Right? To see which is aligning with which. Okay. Now do the example number 3 by your own. Okay. Do the second one in the shortest method. Let's do it in the shortest method. Short method. How? Length of one main scale division, 1 millimeter. How many coincides? 50. 1 divided by 50, 0.02. Verified. Okay. Shortest step is verified to the second example. Let's go to the first example. Understand? You understand? Okay. Go to the first example. 1. So, first example is really obvious. We did it thrice or 4 times. That's an ideal, that's a normal 1 millimeter divided by 10. That's going to be 0.1 millimeters. This is for the first example. Now what we are going to do, which part you are asking here? Please count for the example number 1 or example number 2. Hello? Right. So let's go to the third example. So here, what's the length of one main scale division? Third example is going to be 0. Going to be 0.5 millimeters. Okay. Length of how many main scale divisions? 50 main scale divisions aligned. So length of 50 main scale divisions is going to be 49 millimeters. Length of one main scale division, that's going to be 0. Not 0.5. How? This is a little bit different. Length of 50 vernier scale division equals to length of 49 divisions in the main scale. So here 49, not 49 millimeters. Why? This is not 49 millimeters. That's it. 49 divisions. So one division is how much? It's 0.5. So multiply this by 0.5 millimeters. So this is going to be how much? 24.5 millimeters. Understand? Okay. Now what are they going to do? Length of one vernier scale division. So how many they are coinciding? 24.5 millimeters. So I'm going to divide 24.5 millimeters by 50. Okay, 50. So if I multiply this by 2, this is going to be 49. So 0.49 millimeters. Understand? Multiplying denominator and numerator by 2, this is going to be 100. This is going to be again 49. Okay. Yeah. So 49, you come 2 decimal place the front is going to be 0.49 millimeters. Right. So that's it. So what we are going to do now is you are going to find the least count. What's the definition for least count? The length between one main scale division and length between one vernier scale division. So what's the length of one main scale division? Smallest main scale division? 0.5 millimeters. So I'm going to subtract this by one vernier scale division. That's going to be 0.49 millimeters. So this is 0.01 millimeters. Understand? Okay. Write it. Wrong. this is that much. This is double harder than the example number 2. See which one is aligning with which. 1 over 100. We are going to divide 1 millimeter scale into 100 parts. Shall we do it? Take a small millimeter, zoom it and cut it into 100% and zoom out. So due to usage of digital device and these smart boards, when I see small fonts, small letters in the book, I just do like this. Because of frequent usage of this big one. I use digital stuff. My phone is smartphone. University, I use my tab, and everything is digital. See who is far away, I'm going to zoom. So that would be a good option. Make a lens and zoom out. Okay. The time is really running out after the interval. 7:33. Okay, fine. The examples, right? So just the part remaining in our tute is error estimation. Okay, error estimation. That's in page number 6 and 7. Okay, we are going to jump that off for now and be completed until part. So we have how to obtain readings from instrument consisting vernier caliper. That is really important. So after that, circular vernier scale is same as the things and the screw principle. So this is much more basic to go to a instrument. So let's do that. But taking a reading from a vernier screw principle instrument. Okay. So what did I say in the last class? I said that. Did I bring my pen drive? Good. So there's no time to make it draw a vernier caliper again. So I said that the reading is, the length of an object is the length between the 0 of the main scale and the 0 of the vernier scale. I concluded that 0 of the main scale and the 0 of the vernier scale. So in a real vernier caliper, what they do is when they take this guy, okay, when they're making, they align these two, okay, touch them, okay. After what they do is they erase this. They don't write these zeros here. Okay, they erase it and take a pen and draw a straight line here. So this is going to be the 0. 0 is not going to be again here. It's not here. Okay, it's going to be a little bit offsetted to this side. Okay, so whenever a part of this is worn out, we can see that 0 is coming to the negative direction. But here, when the 0 is here, when it's worn out, the 0 also will get worn out. Understand? So they are not keeping the 0 here. They are going to keep the 0 here, and the next one which is aligning is the 9th and the 10th. Okay, this is how a vernier caliper is. So these are known as jaws, right? So in a vernier caliper, you have two types of jaws. This guy, which guy? This guy has a small part here also, and this guy has a small part here. Okay, what? Which guys? These two jaws. So in a vernier caliper, algorithm this whiteboard is really bad. So there's another jaw here. There's another jaw here. So you can measure from here also. Okay. Okay. I'll draw it from the first. So this is going to be like this. this part here like a scissor is attached to here, and this is like this, and again a part here. This part is attached to, goes like this. The vernier caliper part finishes from here. It's attached to base, and it's going to come like this. Like this. Okay, this is a vernier caliper. So this is a vernier caliper. Okay, so yeah, it's a vernier caliper. This part, this pink color, is one solid part which is moving, which can move here and there like this and this. Okay, this part which is in blue color is the fixed part. The fixed part, it can't move. Okay, the thing that can move is only pink part. So here this is a closed mouth like this, so we can keep a ball here. But here, if we increase this a little bit, this is going to be like a scissor that is broken like this. Okay, and it's going to be, when we open this mouth, this is going to be like this. Why do we want to, can we keep something here? No, it's going to bump away when you tighten it up. Okay, but we use this to measure internal radius of tubes. So what we can do here is, instead of putting something here, we can put a cylinder, a tube here. Okay, a tube like this. Okay, and increase the length. It's going to get fixed. So that's why they have given straight edges in these corners. So I can move this pink, it's going to come again like this here in this place. So here I can keep the cylinder. Little bit, don't understand deeply, understand. So I will bring a vernier caliper. It would be much easier to explain. Okay, right. So this is how a vernier caliper is, right? So we can find internal radius as well as external radius. Okay, so this jaws has some name. This is outer jaws. Why? We are going to see the outer radius of a tube. We can find an outer radius of a tube. These are going to be internal jaws. Why internal jaws? We are going to find the internal radius. Okay, and the next thing is outer jaws in gel. This is outer jaw, this is inner jaw, and this two, which two? This is a little not confusing. This is a little bit much more categorized. I'll use two this color. This is the inner jaw. These two are the outer jaw, and I'll use this color to categorize again. These two are fixed jaw. These two are what jaws? Moving jaws. Understand? Okay. So I can tell you to mark that, label it, but I'm not. Time is not going. I know time is not going. So okay, let's mark it. Go to page number 19 for doing this part, taking measurement from that. So we have to have knowledge on the instrument, right? This is known as a vernier caliper in page number 19. You have a vernier caliper. So mark the inner jaws. This is going to be inner jaws. Inner jaws. Inner jaw. This is outer jaw. Outer jaw. Outer jaw. This yellow part is going to be fixed jaw, and this part is going to be, sorry, this is going to be what? Moving jaw, moving, this is moving. This is going to be moving jaw. Write the jaw part, okay? I didn't write the jaw part. Write the jaw part. This is going to be fixed jaw, fixed jaw, fixed jaw. These are the main parts. And additional to that, there's a small part which is synchronized with the moving jaw. It is synchronized with the moving. That's the internal part. So I'm going to use dotted lines. I'm going to use dotted lines. So there's a small band here, okay, a pin, okay. That pin is integrated to this moving lock. It is integrated to this part. That's it. It's like this. Look it like this. This pink color part is one solid part. Color. Okay. Right. So when I am moving this, this line is going to come out and in. Okay. So now I'm going to tell you how to kill a person. You can take this, go to somebody and you can stab somebody from this. This is really the end of this is like this, a bit like this. It's like a needle. I've stabbed my friends when I'm doing this. Okay, this part is known as, so tomorrow police is going to come. Yeah, you are going teaching them about. This is known as depth measuring. We said this as the depth bar, but here we are saying it as depth measuring. Depth. How do we call in the resource book? Practical. Do you have the resource books? No? Have to tell. How have they? Depth measuring strip. Is it depth measuring strip? Or you can name it as, Mac students name it as depth bar. Why? Why only Mac student? Okay. Depth bar or depth measuring strip, right? Depth or this depth measuring strip. Okay. So what are the other parts? So you have the scales, right? You have the scales. So these are the scales. So I'm going to erase them. But the green color. Here it's going to be the vernier scale, scale, and here it is going to be the main scale. Understand? Right. Vernier scale and the main scale. So additional to these parts, we have some other small tiny parts. One is normally there is a part included from here. It's going from the vernier calipers. This part is going back and coming again upside. So let me draw that part also. That's here, right? So If I again color this from a pink, this and this man and guy going to be 1. I mean, can I draw a dotted circle? No. So let me draw a dotted line. So I'll draw it from pink color. So this is going from backside like this and touching this. Part is going from backside and touching this like this outwards. Understand? So this is going like this. Can you see it? Going from out. Part is going from. So this every pink part is going to move. Okay, not this part. So these stuffs, which stuff? This is we can see them. Those pink color is outside, and this dotted line is side. Inside means not this side or this side. It's inside the vernier caliper. Okay, from here, if we draw a 3D diagram, it's going to be a rectangle box. There's a hole here. This is coming out of this hole. This is going to be like this. So this is not a cylinder. This is box model cylinder. I mean a box part. To be much accurate, I can draw it like this. I think I don't want to draw other stuff. I'll bring a vernier pen show because it's running out of time to explain them. So you have, once you take a radius of something, it's easy to slide that bar, right? So after you take the radius, when you take it and when you're going to read, it's going to change again. Well, some forces from our hand. So there's a small lock here. Once you fix it, you can lock it and take that with the object, or keep the object away and you can take the reading. So the lock is located here. You have a small pin here. That is known as the lock, Mr. Lock, LOC. And this is finely polished, which this bar, this sliding bar is finely polished. So some people's hand just slide over that. So it's really hard to, I mean, it's not that hard. It mistakenly goes away. So hard to touch this because this is that much polish. So for that, make it a little bit friction. They are extruding this part to a curved shape. So this is a part of this sliding. So it is like this part. If you look it from down, it's going to be a small circle with a grip. If you look it from here, from the downward direction, it's going to be like this. A grip in the sense, how to tell a grip? Like in a screw nut. In a screw, you have grips, small intruder, like that stuff. So this is not a perfectly circle. This is going to be like this. Understand? So it's easy to catch. No one will slide from it. So you put your hand, touch here, and make it drag. You can drag it here and there. Keep the object, fix it, lock it, take the reading. But here you know how to take the reading. Still you don't know how to take a reading. Okay, right? So what's the time? It's 51. I think it's easy. The only addition. What? Any part that I haven't mentioned? I didn't say it. Sliding. Its name is sliding. What? Sliding. Known as. So it has a really long name. We need to move the slide. What name is? Sliding ball or something? Not. It's not a ball. So first of all, when I saw the diagram, I thought when we are rotating that ball, this is going to become no, not like that. It's a fixed one. Okay, that is a fixed ball. So name it as sliding sliding nut or something. Just sliding nut, not a nut. Okay, sliding nut. If you can, you want, you can put a dash and write a part used to move the sliding jaw. A part used to move the sliding jaw. So I thought of manufacturing a vernier caliper with a circle which is easy to move, so we can finely adjust it by screwing that ball. We can go here and there. After I thought it, there's a product like that. So recently I thought, like in grade 6 or something, I thought it's hard to take an umbrella from hand. So I thought when I'm becoming an engineer, I'm going to make an umbrella which is going to follow us. It's going to fly over us. And now it's there. It's fixed to a drone, and drone is connected to our phone, and the drone is finding our phone using the Bluetooth distance, and it's going to follow us. Everything is there now. Don't worry. You don't have to invent anything. Okay. So go to page number 15. We are going to find the reading in a much quicker way. Okay. Page number 15. Okay, online students, no any problems, right? Had lunch. You want to leave the meeting? No, just wait. Yeah, a little bit more. Okay, I said that the first you are going to coincide this 0 and this 0. Here the 10 and the 9. So we can move this part. The vernier scale, this is the main scale. We can move this part, right? So the length between this 0 and this 0 is going to be the reading. Right? So let's say this is 1 centimeter. 1 centimeter. There are small division. So, and here it is 2 centimeter. Okay. So now the third and this one of the main scale coincided. So this is going to be third. So 3 multiplied by the 0. This count is going to be how much? 0.3 millimeters. What? 0.3? Yes. It's much larger than 1 centimeter, but still 0.3 millimeters. No. Take reading from a vernier caliper. You should know that we have to add 2 parts. Here, this 0 value will be between 2 millimeters. If it is aligned with a millimeter, let's say it's like this. You have the main scale here. You have the 2 centimeter bar here, 2 centimeter scale here, and this 0 is aligned with this. 0 is aligned with this. This is the 0. Okay. Now let's take it as like this. Let's take it like this. Now we are using the vernier caliper. So the 0 is here. The 0. So the 0 is aligned with 2 centimeters. Okay. So however, they have manufactured to keep a gap here as 2 centimeters. Here it is 2 centimeters gap. They have manufactured it. Then it is 2 centimeters. It should align this. So if the 0 is aligned with 2 centimeters, it's the length is 2 centimeters. Okay. And the 0 is not here now. The 0 is now here. So this length is 2 centimeters and this length is also 2 centimeters. Okay. I said it in the previous thing. So vernier caliper they have manufactured. When these two is coinciding each other, when these two are coinciding each other, they have coincided the 0. So when this is moving 2 centimeters, this is going to align with the 2 centimeters. This 0. Understand? Okay. Moving, when it's moving 2 centimeters, it's going to show 2 centimeters. So what here we are doing is, so let's take, this is the main scale, this is the vernier scale. Okay. Now let's tell that this is 19th millimeter, and here this is the 20th millimeter equals to 2 centimeter. Okay. Now here's how much gap? 1 millimeter gap. But the length is here. So this is 0 and this is the 0. As per the theory, the length between these two should be the length of that object, right? Okay? Length between this should be the length between two jaws. That means the length of the object. Okay? Let's assume that there's no any 0 error instrument. Okay? So the length between these two jaws should be the length between this. All right. Okay. So we know that from here to here, it's going to be how many millimeters? 19 millimeters. But we don't know this gap. Which gap? This gap. Not right. We don't know this gap. Why? This is 1 millimeters. We can't read less than 1 millimeter. For that only we are using the vernier caliper. Now what we are going to do? We are going to see which of the vernier caliper is coinciding with the main scale, right? Okay, and we are going to count 1, 2, 3, and 4. Let's take the fourth one coincided here. Let's say the fourth one, the fourth aligned here. So what's the number of division that's aligned? Number of vernier divisions? 4. So 4 into 0.1 is equals to, this is the least count, right? This is the least count, normal vernier caliper. So it's going to be 0.4 millimeters. Okay, so this gap is going to be 0.4 millimeters. Understand? So the final reading is, what's the final reading? Final reading is maximum that can be, maximum that we can read in main scale. What's the maximum we can read in the main scale? 19 millimeters. Okay, that's readable, right? That's readable. So that plus the vernier scale calculated part, vernier calculated part. So understand? Okay. So this vernier calculated part divides into two: vernier coincided part multiplied by the LC. What's LC? Least count. So finally, how we are going to take the reading? The readable part of the main scale, add to the coinciding division of vernier scale multiply by least count. Understand? Okay, right? So understand, right? So in the final page, in the final part of the book, you have to fill it. So fill it like this: reading of the main scale. This should be reading of the main scale. This should be number of vernier marking coinciding with the mark of the main scale. Number of vernier divisions coinciding or aligning with the main scale, You can read this white part, right? White color. Number of, I can't read it. Number of vernier. This is vernier, right? Vernier divisions. Vernier divisions coinciding with the main scale. Number of vernier divisions coinciding with the main scale. And this is going to be the least count. And the next page, you have a small blank. So look at your friend's book and copy those things down. So let's fill in that blank also. That's going to be like this. So I have given you an example in page number 15. Okay, I'm going to take the reading from that. Okay, go to that object. You have that object like this, and it's upside down. Here is the vernier scale, and there's an object, this object. So what's the reading that you can take from the main scale? That's how many millimeters? 12 millimeters. Can you count it out? Okay. In the main scale, you have one here, that is centimeters. And after that, And after that, you have this is the 10 millimeters, 11 millimeters, and 12 millimeters. After 12 millimeters, so before 12 millimeters, the vernier is here. Vernier in the sense the zero scale of this. This is the zero scale. Okay. So up to here we can take from the main scale. How many millimeters? It is. How many millimeters it is? This is 1 centimeter. That means 10 millimeters. So this is 1 millimeter gap. That's 1 millimeter. So from here to here, it is from here to this point. It is how many millimeters? How many? 11. Object. Just look at it here. This is 1, and here this is the zero scale. So draw a line directly from here. So it's going to be between the 11th and the 12th, right? Okay, understand? So until this 11 we can take from here. Okay, so what we are going to do is we are going to add this and add this part. So this is the reading that we are going to take from the vernier caliper. Understand? So the maximum that we can coincide with the vernier caliper is 10 divisions, right? 10 divisions. 10, no, there's no any other parts in the normal vernier scale. 10 multiplied by 0. It's going to be 1 millimeter. 1 millimeter. So the maximum we can read from our vernier scale is 1 millimeter. So between these 2 millimeters, we are going to take this millimeter, this part. I'll draw it in next another color. This part, this red color part. So this yellow color part, from here to here, we are going to take from the main scale reading. From the main scale reading. From here to here, we are going to take from the main scale, and from here to here, this is the 11th, this is the 12th, this is the 12th, this is the 11th, but this length we are going to calculate by the vernier part. Understand? Okay, right? So now we know the main scale, it's coinciding 11 millimeters. I'm going to add how much is coincided. So see which vernier scale is aligned with the main scale. It's going to be the 1, 2, 3 and 4, fourth one, right? I have put an arrow. Have I put an arrow there? Yeah, there's an arrow. There's an arrow. That's the fourth vernier scale. In the vernier scale, 1, 2, 3 and 4. 4 is aligned with the main scale. No other vernier scale is aligned with the main scale. Just look. Just have a look. No one in the vernier scale is aligned with one of the main scale division, right? So this is 4. So how many number of divisions are, which number is aligned with the main scale? Fourth division, right? So what we are going to do is 4 multiplied by 0.1. 0.1 is the least count. So this is going to be the reading millimeters. So 11 millimeters multiplied by 0. Sorry, not multiply. It's going to be plus add 0.4 millimeters. So this is going to be 11.4 millimeters. The answer. Okay. So in that space, what you have to do is you have to write like this. You have to write E is equals to E is equals to 11 millimeters plus 4 into 0.1 millimeter. This is equal to 11 millimeters plus 0.4 millimeters is going to be 11.4 millimeters. Okay, fine, understood. So on from the vernier scale, what we can do is we can only measure the measure between 0 and 1 millimeter. Only 1 millimeter we can measure from the vernier scale. The maximum is 1 millimeter. Understood? Right. So let's put a night class and complete the other. There's a small part, and we are going to start vectors the next week. While the vector is going on, we are going to put night classes to complete this practical part. Okay, then bye, online students. Have a nice day. Yeah, thank you. Bye. Okay, can leave. Wait. Okay, bye. Can leave.